I'm really still not used to that. So the population in Kenya is 18.9 million in 1984 and 46.1 million in 2015. Assuming exponential growth, find an equation for the population of Kenya as a function of time. So essentially the population is going to be our y values and our time value is going to be our x value. In years since 1984. Now I need to make a specification here. It says assuming exponential growth. And that's a terrible box because I just drew it right through what I need to talk about. If you reread this question, nowhere does it say the word rate, and nowhere does it say the word continuous rate. So since it has neither of those phrases, we get to choose. So since we don't have rate or continuous rate, we can choose. That's only very rarely going to happen. Most of the time it's going to be set because you either have the word rate or you have the phrase continuous rate. But in this case, all it says is exponential growth. It says nothing about rate or continuous rate, so we get to choose. Now I'm going to choose to use the e to the kt form because this is similar to the wolf example in 1.5 where we had, the 2 points and we had to write the equation using those 2 points. And it was about reintroducing wolves to Wyoming or something like that. So since we've already done one like that for an a to the t form, I want to do it in an e to the kt form. So that's why I'm choosing to use e to the kt here. So this is essentially that same idea of we have 2 points and we want to find the equation of, well, the exponential equation. So what are the 2 points we have? Well, we're taking t to be years since 1984. So if we consider 1984 and 18.9 million, that's going to tell us 0 and 18.9 because 1984 is 0 years since 1984. And then 2015 is 31 years since 1984, so 31 and 46.1. And so just like with the wolf example, we do kind of have a slight shortcut here. And I'm going to take half of the shortcut, but then do the rest of it full out. So we have P0 already. So that's half of the shortcut we could take. And that's the part of the shortcut I'm going to take. P0, again, is still just the value for when t is 0. So that's going to be 18.9. So how do you know which is the x and which is the y? This phrasing right here. Let me do it in another color. Red. Find an equation for the population of Kenya as a function of time. So population as a function of time, essentially saying that exact same thing, but cutting out some of the fluff. So let's say our population we're going to name P. You kind of treat that as an equal sign. Function gets you the F, and the F, it's lagging a little bit, of time. So that phrasing, population as a function of time, essentially gives you this function notation if you just kind of write it down as you read it. And so if you remember that it's usually y equals f of x, that means that our t values are going to act as our x's and our population values are going to act as our y's. So you kind of need to pull out from the question, what is a function of the other thing? So I'll leave that up for a couple of seconds, but then I'll need to erase it because I need the space. So where was I at? P0, we know what it is. It was 18.9 million. If we didn't know it, we would have to find it, and I'll make a side note of where that would need to happen when we get there. So I need to erase this thing I just wrote. I'll leave it up for another 5 seconds. Okay, so now what we have to do is we essentially need to solve for k. We know what P0 is, and the other thing we don't know is the k value. So what we did with the wolf example and what we're going to do here as well is whenever you have 2 points and you want to find the equation, the way that always works, again, there's sometimes a shortcut, but I'm not going to use it. The way that always works is you're going to write both of the points in this form. You're going to use the one with the larger t value first. So that's going to be the 31. So we're going to have 46.1 equals, I know what P naught is, but I don't need it right now, so I'm just going to keep it generic. If you want to put the number in there, that's totally fine. And then I have K times 31. And then my other point would give me 18.9 equals P naught E to the K times 0. And hopefully the fact that we divide these two kind of rings a bell. Maybe not, but that was our next step. Is the reason we write these two like this is so we can divide them, because that gets rid of this P naught and just leaves us with one thing that we can solve for. So 46.1 divided by 18.9 will give you 2.43915. That's one thing I'll say for the homework. If you haven't gotten this one of these, nope, blah, blah, blah. In this section, it's important not to round until the very end if you can avoid it. So I'm taking a decent amount of decimal places here, because if I kind of round too soon, it's going to throw my answer off. If this was an exam or a test, that would be fine. But with Wiley is so particular and doesn't always have a large enough tolerance to deal with that. So you want to try to take as many decimals as you can along the way and then just kind of round at the very end. But if we have two things with the same base and we're dividing them, we're going to subtract their exponents. So I essentially have 31k minus k minus 0k. So that's going to leave me with 31k. That's a very gross looking k. So that essentially gives me that. That still looks not like a k. There we go. And so now I want to solve for k. I'm once again in a situation where I need to use natural logs, because the thing that I want to solve for is in an exponent. If I can do two steps at once, if not, if it freaks anybody out, tell me to do the intermediate step. But I essentially took the natural log of the right side and pulled that power out at the same time. Natural log of e is 1, so we can essentially forget about it. So to solve for k, we're going to divide both sides by the 31. This will approximately be 0.028763. I'm going to cut it off a little bit for the actual answer, but that is what the decimal would turn out to be. Side note, if we didn't have P naught, this is where we would have to solve for it. And if we wanted to solve for it, we would essentially take one of the two equations and plug in the value of k we just found. So I'm just going to take 8. I ran out of space. I need to back this up a little bit. So if we needed to solve for P naught, we would do so by plugging that k value we just found into one of the two equations, whichever one makes you happier. They're both going to get you the same answer at the end of the day. I'm just going to take 288 times 31, and you'd have to solve for P naught. But we have P naught here, so we'll just use it. So our equation, P naught is 18.9, e to the k, 0.0288t. 0.029 is fine. 0.03 is probably a bit iffy. If it was an exam, I would accept it, but Wiley would probably definitely get angry. Also, triple check, Wiley usually specifies how many decimal places they want. Questions, concerns on that? Do you mean if I solved for P naught? What did I just do? Oh, sorry. My being everything else in the setup here is obnoxious and it's pressing things when I don't want it to press things. If you use the A to the T form, can I do that really super quick in my brain? It would essentially turn out to be the equivalent form of this, but if I think about it really super quick, so 46.1 divided by 18.9, but then you would have had to take the 31st root. So if I did that correctly super quickly, it should, 18.9. I'm getting something like 1.029 to the T. Which again, these should technically kind of be the equivalent forms that we were looking at the other day. There might be some rounding errors, but should technically give you equivalent forms. I'm going to erase that now so that people looking back at this later don't get confused. But that would be your other 18.9, 1.029 to the T. I'll leave it up there. 5 more seconds. Okay. We talked about half-life and doubling time the other day. I'm just going to say something about it again, just really quick. On your homework, you have a couple of these. Remember, you don't need P0 for doubling time and half-life. Because if you want doubling time, you just want to solve something like 2 P0 equals P0 A to the T, or P0 E to the KT if you're in the continuous form. So read the problem and see which one you're working with. And then half-life. If you have P0, you can still do it. It's not like you can't do it when you have P0, but you don't need P0 because you can just set it generically equal to either half or twice what you started with. So we did one of those the other day, so we'll move on. We also gave a introduction to the idea of interest, but we didn't get around to doing these few examples, which I did say we pretty much have everything we need to do these. We just hadn't put them in the context of interest. But let's look at these really quick. So a reminder, we have interest compounded annually or continuously, which essentially goes right to either the original or the continuous form. So it's kind of working the exact same way. If you see the word continuous, it's the E form. If you don't see the word continuous, then it's the other form. So say a bank advertises an interest rate of 2% per year. If you deposit $10,000, how much will you have in 3 years' time if it's compounded first annually and then continuously? So annually is essentially going to be the A to the T form. It's usually written out as 1 plus R to the T when it's in terms of interest, but it's the same idea here. So our P0 is our 10,000. That's not how you write 10,000. And the R in this case comes from the 2% per year. The 0.02, which makes the A value 1.02. I realize I'm talking really fast and I should probably slow down a little bit. So essentially the equation we want to plug into is 10,000, 1.02 to the T, and since we want to know 3 years later, we're going to want to plug in 3. Plug that sucker into your calculator. And now I got rid of my notes again. This will come out to be approximately, whoops, down here, $10,824.32. Whereas opposed to compounding continuously, now we are in the E to the KT case. Well, it's presented as E to the RT when it's in terms of interest, but it's the same idea. So our R here is once again 0.02 and our P0 is still 10,000. So in this case, things are getting a little cluttered. We have 10,000 E to the 0.02 T. Again, in the e to the kt form, we don't manipulate the rate at all. We just put it in as it is. So I want to know 3 years later. Punch that sucker into a calculator. And you get $10,832.87. Also, so here I'll pause and I'll talk about, in case you don't know what the difference between the two actually is. And the difference between the two is how often the interest is kind of put onto the account. If it's annually, it's just going to be put on at the end of the year. And if it's continuously, it's just going to be, it's essentially accruing interest every single millisecond it can. So there's also, you know, monthly interest, daily interest, weekly interest. So there's things that could compound interest every month, every week, every day, every hour. We don't consider any of those. We just consider, is it compounded once a year, or is it compounded essentially every single second it can? And no, there's not a huge difference between these two numbers, but 2% is pretty, well, it's pretty good for interest, if I'm honest. But in terms of just being a percent, it's pretty low. And also, I know $10,000 seems like a lot of money, but in terms of interest, it's not. So if we had a larger amount of money, or especially a larger interest rate, this difference between the two would start getting much larger and much more easier. Well, this is easy to see because they're different numbers, but it would start getting much larger, the difference between the two equations, especially as the interest rate increases. If the P naught increases, it will make a difference, but not as much as if the rate would be increasing. But they do differ, of course, because they're not the same number. And of course, the more times, you know, a day, a month, a year, that the interest is being compounded, the more money you're going to have. You always want it to be compounded kind of as much as possible. So anyway, in case you didn't know what the heck these were actually, what the difference between the two was. So last one in 1.7. If $10,000 is deposited into an account, paying an interest rate of 1.5% per year, compounded continuously, how long does it take for the balance to reach $12,000? So we've got an initial of $10,000 again. Now we're told continuously, so we're in the e to the kt form. So we've got e to the, oh Lord, I always have to do this again. 1.5 is going to become 0.015. So 0.015 t. And we're asked, when is the balance going to reach 12,000? So we want this value to equal 12,000. K is the exact same thing as R. Yes. If you want to think about them as being the same exact thing, that's pretty much R. It's just presented as a different variable because that's how the definition has been presented for forever. Anyway, so to solve this, we want to solve for something in an exponent. So this is when we pull out our logarithm process. So we've got to isolate the exponential first. So divide both sides by that 10,000. That's going to be 1.2. I'll touch on that in just a second, Jamie. So now we have to take the natural log of both sides, and if I can, I'm going to pull the power down at the same time. Again, if anyone wants to see that intermediate step, just let me know. I'm just trying to be lazy, but I cannot be lazy if you need me to. Natural log of e is 1. So to solve for t, we have to divide both sides by the 0.015. Which will turn out to be approximately 12.15. My pen's not working. Come on. Oh my goodness. 1548 years. So it'll take approximately 12 years before their $10,000 will be $12,000. When we are showing work on the exam, will you take off if we don't put the same variable in, but we do it right in the answer? So yes, but a minuscule amount, like maybe a half a point. Now, the other thing is, if you, like, say you're doing the equation of, let's jump back to linear really quick. And, you know, the original thing is given in terms of P's and Q's, and you're given like a table and you want to write the linear equation. Say you're doing all your work in terms of Y's and X because you prefer Y's and X's. And then you write, so say you would come out to whatever your equation you found would be. Let me put a number in there. If you left it like this, I would probably take off like half a point. Because technically the correct answer should be in terms of the correct variables. But if you want to do all your work in terms of X's and Y's or whatever variables you prefer, but then at the very end, you switch back to the actual variables they should be, that'll be perfectly fine. I don't care about that as long as your answer has the correct variables. Because it is important to work with the correct variables. I know I might seem a little semantic, if you will, but it's not something where I'm going to like mark the entire thing wrong, of course, because if you're doing the process right, that's the main thing I care about. But I might take off maybe half a point if I'm feeling sassy, which usually I do in those cases. But it's not something that would be tanking your grade in any way, shape, or form. But it's just good notation to use the correct variables. Any questions about 1.7 in terms of the notes before I move on to 1.8? Again, hopefully we'll have a little bit of time at the end to talk about questions in general, like the homework or whatever. But if you have any questions about the notes we just went over, let me know. Otherwise, we'll move on to 1.8. I started recording, right? Yes, I did. Jeez. All right. Doubling time? So yeah, so say, let me just pull one real quick off the top of my head. Let's say population, there's one like this on your homework. I can't spell. Population is, let's say decaying. No, let's do increasing, because we did half-life the other day. Increasing at 7% at a rate of 7%, find doubling time. So this is a very simple, simply phrased, I should say, simply phrased question. But there is a similar one on your exam, on your homework. So population is increasing at a rate of 7%. Find the doubling time. I don't see the word continuous anywhere, but I do see the word rate. So since it doesn't include continuous, but it includes rate, I know I'm in the A to the T form. Once again, for doubling time and half-life, you do not need P0. If you have it, that's awesome, but you don't need it. What I do have here is we have that R is 0.07 because that's what 7% is as a decimal. So if A is equal to 1 plus R, then A is going to be 1.07. So I know that the function I'm working with is P0 1.07 to the T. Don't know what P0 is, but again, don't need it. Because doubling time is asking for how long it's going to take for this initial value of P0 to double. And I can just generically write down, well, it's going to be twice whatever P0 is. And the reason that's okay is because the first step we're going to then do to start solving this. Okay, so let's see. You might have rounded a little too soon. No, there's not a lot of rounding in this one. Let me just finish it out and we'll see. And I can look at it later, Brianna, because sometimes Wiley's being a jerk. Sometimes the notation's just off. So the first step we'd want to do here is divide by P0. And all the P0s go away. That's why we don't need it. So we have 1.07 to the t equals 2. Take the natural log of both sides. Should leave that in. Natural logs allow us to bring the power outside. Divide both sides by the natural log of 1.07. I don't know what that is. Natural log of 2 divided by natural log of 1.07. And you'd get approximately 10.245, let's say. Exactly, JD. Half-life would be the exact same thing. The only thing that would change is that we'd have a 1/2 here instead of 2. Exactly. All right. So 1.8. We're gonna just go over half of it. So I'm scrapping half of 1/8 because it won't be important to us later. But this idea we will need to kind of come back to once we get to chapter 3. So we need to see it. So this is about something called the composition. So we're given functions f and g where the range of f is contained in the domain of g. We define the composition is formally usually written as this, kind of this G circle F idea. 99% of the time, you'll see people use this instead. And that's the one I constantly use because I think it makes more sense as to what's actually going on. And essentially what the composition is doing is it's taking one function and plugging it into another function. So we're taking a function and plugging it into the other function. Now I want to make a note about this range of f is contained in a domain of g thing. In terms of our class, we don't have to worry about it too much, but just in case you're curious about what it's actually saying. So say I had two functions and they were this. And I wanted to compose them together, which would mean that I would have to plug one of them into the other. Well, if I look at what I get when I plug in +1 into f, I would get 1 minus 1, so I'd get 0. And what you'll see in a minute is the composition would then say that I would need to plug this 0 into G. That's what the composition would be telling me, and I know I haven't explained the composition quite yet, but that's what it would be telling me to do. And if I were to plug 0 into G, I would get 2 over 0, and if you don't already know, you can't divide by 0, it makes everything explode, and it's not possible. So essentially what this little phrase here is saying, where the range of f is contained in the domain of G, is essentially saying that it needs to be able to work. So if we were to compose these two functions together, I would essentially need to say, but I can't be equal to 1 because that would give me a 0 that I have to plug in, and that's not possible. Again, it's not really something we have to concern ourselves with very often at all. But that's kind of what that's saying, is that if you get a value out of f, you must be able to actually plug it into G. But anyway, so let's see how this is going to work. And I like to start off compositions a little stupid. So I know that, I've got an f of pancake down there, and that might seem a little stupid, but I have a reason for it. So this is kind of the idea behind a composition. This first example aren't quite formal compositions, but it kind of gets the idea across, hopefully. So if I have f of x being 2x squared plus 1, and say I asked you to plug in 1, well, you could tell me the number that you get from that. But if you think about what actually happens when you plug in 1, you would get 2 times 1 squared plus 1, right? And then you would actually figure out what it equals. Well, what if instead of plugging in 1, I asked you to plug in a plus symbol? Sure, that doesn't make a lot of sense in terms of actually calculating the math out, but I can ask you to do that. I can ask you to plug in whatever the heck I want. That's kind of the point. And if you were to do that, then you would have 2 times plus squared plus 1. And again, that doesn't look like something you can actually calculate because it's not. But what you've done is you've taken, I'm asking you to input a plus sign everywhere you saw an X. So you just go ahead and do that. And I can continue to ask that for the stupidest of things, like pancake. I can say, what is f of pancake? And then this would say that the input, so everywhere I originally see an X, is now going to become a pancake. So 2 times pancake squared plus 1. So kind of the meat and potatoes, if you will, of compositions is essentially saying you're taking something more complicated than just a number or an X or a Y, and you're plugging it into another function. So what if I ask for f of x plus 1? So that's telling me that everywhere I used to see an X is now going to become an x plus 1. So that would turn into 2x plus 1 all squared plus 1. Also, I highly suggest always taking the parentheses with you. Kind of just treat it as one entire thing. You're taking the parentheses with you as your input as well. Sometimes you don't need them, but even when you don't need them, it's perfectly fine to have them. So I would just suggest always putting parentheses around whatever you're inputting. Questions behind that idea before we make it a bit more formal? All right. So the inside function of a composition is the calculation done first, and the outside function is the calculation done last. Now, kind of the other way to think about it is here we have something that we're plugging into something else. The thing we're plugging in is the inside function, and then the function that we're plugging into is the outside function. So like say I go back up to this example 4 right here. Well, x plus 1 would be my inside because that's what's being plugged in. And then if we think about what f of, the function f actually is, that's the 2 squared plus 1, that would be the outside. So it's not just about calculations done first. There is a bit of that. We'll get to that. There's an example at the very end where we actually get out numbers instead of formulas. And that makes a bit more sense to say calculation done first. But we also have this idea of what's the thing we're plugging in and what's the thing that's being plugged into. And that idea is going to be the most important thing that we pull again in chapter 3, is this idea of outside versus inside function. So let's look at a few more formal compositions. Well, the first column isn't really formal compositions. The second column is. Let's say we're given that f of t is t squared and g of t is t plus 2. So this first column is kind of what we were just looking at. What happens if I plug in t plus 1? Well, if you think about it, f of t, so the function f is telling me take the input and square it. Whatever is the input, it's just that input squared. So if we're plugging in t plus 1, we're taking t plus 1 and we're squaring it. Most of the time, I will never ask you to simplify these. You can simplify them if you want, but please, for the love of all that is good and holy, this would reduce to this. You'd have to FOIL it out. It'd be t plus 1 times t plus 1, and you'd have to distribute and all that jazz. For the love of all that is good and holy, I'm writing it in red because it's not right. Please do not say that this is equal to t squared plus 1 squared, because it's not. Don't do it. Not okay. You'd have to FOIL it out. But again, 90% of the time, 95% of the time, I will never ask you to reduce and simplify. So when in doubt, just leave it. But anyway. Now, number 2 actually isn't a composition at all, really. Because if you notice the positioning of the parentheses, the plus 3 is kind of just tacked on at the end. It's not actually being plugged into the function f of t. So this is just telling us to take the function f of t, which is defined to be t squared, and then just tack a plus 3 on the end. So that one kind of gets thrown in there to try to throw you off. That's not really a composition, but really the difference there is what's in the parentheses. Since the +3 is not inside the parentheses, it's not getting plugged in, it's just being tacked on the end. And then f of t plus h is somewhat similar to the t plus 1, is we're essentially taking the entire thing t plus h and plugging it in. So since the function f tells you to square whatever you put in, we'd have t plus h all squared. So now let's make this a tiny bit more formal with some actual full-blown compositions. So here's kind of what's more often asked, is find f of g of t. With compositions, work inside out, inside out. So the first thing you want to focus on is this g of t. Well, what is g of t? So let me rewrite this. So I have f, and then if I think about what g of t actually is, g of t is defined to be t plus 2. So let me just go ahead and rewrite that function name in there. For number 1, I would accept either of these two forms. Personally, most people will stop here, which is perfectly fine. If you want to reduce, then this would be the correct answer. So the thing in red is not the answer. Don't do this. No. So we kind of replace g of t with actually what it's equal to. And now we kind of look like something we were already focusing with over here, where we want to plug t plus 2 into the function f. So we'd get t plus 2 all squared. Also, this is kind of an intermediate step. If you get good at these, or you just already know how to work with these, you don't have to write down the middle step. You can jump from one end to the next if you already know how to do it, or you get really good at them. It's just, I feel like that middle step kind of helps in the beginning to kind of see how this is, what's happening here, instead of just jumping straight to the answer. In number 5, inside out, so we want to focus on the f of t first. So let me rewrite this. So I've got g, and then I'm going to rewrite f of t as what the function actually is, so that's t squared. This one. So where did that squared come from? We are taking t plus 2 and plugging it into the function f. So since, why am I still in teal? Well, I guess just, so f of t is t squared. So if I'm instead plugging in t plus 2, it'll be t plus 2 all squared. No matter what I'm plugging in here, that thing is getting squared. Does that make sense? Okay. I'll leave that teal there for a little bit, but then I might erase it because if people are looking at it later, they might not know what's going on. So now here we have g of t squared. So we want to plug in t squared into the function g. Well, g tells me that whatever my input is, it's that input plus 2. So if my input is t squared, we'll have t squared plus 2. And then number 6, inside out. Now this is using the same function, so we're plugging the function into itself essentially. So there's going to be lots of g's floating around. But we have g, and then, well, what is g of t? G of t is t plus 2. So now I'm saying let the input be t plus 2, plug it into the function g. Well, g tells us that you have to take the input and add 2 to it. So if the input is t plus 2, we'll have t plus 2 plus 2, which you could, of course, reduce to t plus 4 if you wanted to. But again, I don't really ask you to simplify these, so I'm going to erase this. Questions, concerns on that? Okay. Okay. Let's do that again with different functions. So I'll try to leave those up. So now let's change up our functions. Now we have e to the x and 5x plus 1, and we want to do some compositions. Inside out, first thing you want to focus on is this g of x. So g of x, I'm kind of going to write backwards, but hopefully it'll make sense. So we essentially replace that g of x with what the function actually is. And then this is saying the input of the function f is going to be 5x plus 1. Well, my f of x is telling me whatever my input is essentially the exponent of this e. So I have e to the input. So that will make this e to the 5x plus 1. I'm taking that entire, and let me just put it in parentheses because I started saying take the parentheses, and then I've been dropping them every once in a while. All right, I'm going to keep pausing after each one slightly and let me know if you have questions, or just tell me to go back to a different one or something, but I'm just going to keep chugging along every once in a while. So the next one, inside out. So first thing is let's rewrite f of x with what it actually is equal to. So we'll rewrite this as g of e to the x. So the function g tells us whatever our input is going to be multiplied by 5 and then added to 1. So 5 times the input plus 1. So 5 times e to the x plus 1. These last two are kind of plugging the function into itself, but still work inside out. So f of x is equal to e to the x, so we can rewrite this as f of e to the x. This is probably the one that looks the weirdest because the function f is telling us that our input is going to become the exponent. Oh, that dropped my pen. So if the input becomes the exponent, but our input is e to the x, it's going to give us e to the x. And I'll keep the parentheses. I believe this is hidden. We might not have time for questions, but I'll try. So here, g to the x, replace it with what it is, 5x plus 1, so that we can rewrite this as g of 5x plus 1. So if g tells us 5 times the input plus 1, 5 times our input plus 1, but our input here is 5x plus 1. You could expand that and simplify it a little bit, but again, I almost never ask you to. Questions, concerns? Okay, let's wait a couple more seconds, maybe just 5 more seconds, and then I'll scroll down. Okay. Okay. I'm going to skip example 4 just in case we run out of time, because example 5 is more important. And we can kind of come back to example 4 later in time, but this one's more important. So now we have a table And we still have these compositions going on, but now we're going to end up with just plain old numbers instead of a function. And if you're wondering how to read this table, say you want f of 2. Well, here's the values of f of x at x equals 2. So you kind of just, go and meet yourself on the table. So again, inside out. So the first thing I'd want to calculate is f of 0. So f of 0 would be 3. So I'm going to have that this is equal to g of 3. And then if I look for g of 3, that gets me that my value is 6. First thing I want to calculate is g of 0. G of 0 is coincidentally 0. Oh, no, I messed up. Sorry, f of 0 is what we can rewrite that as. And then f of 0 is 3. Same idea for the rest of them. Maybe I'll try to save a little bit of time and not switch the colors. If the colors are really helping, just let me know. So g of 1 is 2. And then f of 2, so g of 1 gave us 2, and then f of 2 gets us negative 1. F of 1, well, that will be replaced with f of 1 is coincidentally 1. G of 1 is 2. F of 0, we can replace f of 0 with 3. And then we're asked to find f of 3 then, because we're working inside out. F of 3 is negative 3. G of 0 is coincidentally 0. And then we also want to find g of 0, which is also coincidentally 0. Questions on that? Yep. So once I replace g of 1 with its value of 2, then I want to find f of 2. So my f of x values at 2, go and meet yourself on the table, will get us negative 1. Any more questions on this idea? Okay, then I'm just going to scrap number 4. We'll come back to the idea of it when we need it again. For the sake of time, just so in these last 15 minutes, I do want to give you guys some time to ask me questions on the homework if you have any. So we'll take the last 15 minutes to do that. We'll just come back to the idea. I can put the answer to example 4 up on Blackboard if you want to look at it. It's essentially going backwards. We start with the composition and we want to break it up into 2 different pieces. But again, we'll come back to that when we need it again. So if anyone has any questions they'd like to ask on, sorry, these really hurt my head, on the homework, or you want me to go over a certain topic that you're feeling really scared about, or something else. I guess, how many points does each question usually? Oh, That's a question. So I haven't written the exam yet. That's happening right after this. So there's usually some multiple choice questions, which are usually 4 or 5 points apiece. And then, so there's usually, this is a 75-minute class, so it'll be slightly longer than my other one. So maybe 12 to 15 multiple choice, and then there'll maybe be 5-ish, 4 to 7 maybe free response. And those can really range. They can range anywhere from like 5 to 12, or some of them get up to be like 24, but usually in that case it's like question 5, part A, part B, part C. So, and like each part is only worth 8 points. So it can kind of range. It's similar to my quizzes, if you've been paying attention to the point values. But yeah, so the multiple choice are all either 4 or 5. I kind of flip back and forth every semester. So Nicole, I'll get to your question in just a second. For the study guide of the exam, will it be similar or different to the exam? I would say that the study guide that I created, not the one on Wiley, is going to be similar to your exam. You'll see similar types of questions, not exactly the same types of questions, but similar topics and stuff like that. The review packet has multiple choice, it has free response, and the packet also has 3 questions where essentially I give you the work for the question and you have to tell me where there's an error, if there is an error. There will be some like that on your exam as well. So I would say that the study guide will be pretty decently similar to your exam. The study guide is probably a bit longer, I would say, but similar. Okay, so let me start getting these questions. In terms of the thing that came in. So on question 46, I'm going to keep saying my equation wrong. What is the equation to solve the Okay, so it's probably your notation. I will pull that up in a hot second when I can. There's the next one. I wrote a question in chapter 1, blah, blah, blah. I got would be yes, the exam is normal time, normal class time, same bat time, same bat channel. While I'm pulling up my Wiley, the exponential function, what does the A represent? So the A represents, where's my OneNote? So the A, why is this green? So the A is what's called the base. And essentially, if you look at some exponential functions, and let me do one that's not terribly hard to see. Let's say 2, 4, let's change this to 6. 2, 4, 8, 16, so that would be 64. So essentially, if you look at these y values are being multiplied by 2 each time. Well, here it's being multiplied by 4, but notice that this goes up by 2. So if you consider it in steps, the first step would be multiplying by 2, and then the second one would be multiplying by 2. So what the base is essentially this number that we're multiplying the y values by to get the next one. So that's kind of what it's, how can you tell if it's exponential? I will get to that in a second. Let me get back to Nicole. So if you are a person who doesn't think they have any questions or doesn't want to stick around to see what the questions are, you are free to leave. I'll spend this last now 10 minutes looking through some stuff. So let me see, Nicole. Where is it? Where is it? There it is. Okay, yeah, no, this is a big thing. Wiley, if you want to type in an e to the something form, put parentheses around the thing and include the t in it. So you could also write this as like e to the 0.07 times t. but it's just the important bit is that these parentheses need to get in there. So if you fix that, and I can fix the point values for that, Nicole, but just go ahead and get that counted as correct, and then I'll go back and I'll change it later. I'll make a note of that so I remember. I have a question on chapter 1, blah, blah, blah. 25 to 28. 25 to 28. Sydney, I will make note of that, and I will go back as well and do that one. 25 to 28. Can you pull this up for me, please, Wiley? Goodness gracious. What are you doing with your life, Wiley? Wiley, do the thing. Oh, my Lord Almighty. Oh, I should really. Sorry, just get my nails on. I will look at it in just a second, Rihanna. Where am I? Sorry, Savannah Shaver. I'm getting there. What? Okay, so just tiniest bit off. So, oh, no, wait. Okay, nope. Different than what I thought it was going to be. Okay. So you found that your A value was 0.8, and you now want to know the rate. You're asked for the rate of decay. And it's good that you recognize that it was decay because that's less than, the A value is less than 1. So say you want the rate. So if A equals 1 plus R, then R would be equal to A minus 1. So if your A was 0.8, if we subtract 1 from that, we get, well, I should be able to do this in my head, but let me just stretch it. Negative 0.2 is equal to the R value. But since it wants the percent, we would have to change this over to a percent. Now, since it says decay, we don't need to worry about the negative, but this would turn into 20% decay. So you're looking for the 20% here. You didn't want the base, you wanted the rate. So if you ever see the A value, that's going to be associated with the word base, and the R value is going to be associated with the word rate. So you said 2%, so it just should have been 20%. I didn't finish reading the rest of your question. Already answered that. How do you tell when it's exponential at a table? Oh, dang it, what have I done? Rihanna, I do have free time tomorrow, and I can send you, oh no, wait, it's past, oh no. You can send me an email of the ones that you want me to look over, but it might take me a while to get to them because I have things that I need to do after class, but I can try my very hardest to get back to you tonight on that. What was I about to do? Tables, how can you tell if they're exponential? So what do you want to do with a table? 1, 2, 5, 6, sure. So let's think of something that's not exponential. So let's do 2, 3, 5, 7, sure. So if you're looking to see if it's exponential, what you want to look at is you want to look at ratios. But sometimes you're going to have to take a kind of gross looking ratio. We're going to have to consider something that looks like this. So this is kind of the first thing we did when we looked at 5-1. Now, this looks scary, but let me explain what it means. So this would just be the difference between the x values that you're looking at. So if you don't have consecutive x values, we need to bring in a root. If they're consecutive x values, you just need to worry about the ratio. So say I wanted to look here and I wanted to see if it was exponential. Well, from 1 to 2, that's just increasing by 1. So I just want to look at the ratio. So I'd take the y values and I would divide them. Excuse me. Well, this is 1.5. And then I would want to compare that to the next ratio. Well, in the next set, I increased by 3, so I am going to need to bring a root in. So what I'm going to do is I'm going to take the ratio of my two y values. But since the x values differ by 3, I'm going to have to take the cube root of that. And if that matches the other number, then I know it's exponential. But this number is definitely not going to match. It's 1.1856, blah, blah, blah. So since these numbers don't match, this data wouldn't be exponential. So what would it look like if it was exponential? I know I'm going through this kind of quick, but I'm trying to get to as many of these as possible. So say we have 1, 2, 5, 6 again. Let's do 7. Let's go by 2. And let's say I do, oh Lord, 1/2, 1, 8, 32. I hope I did that right. So if we want to tell if this is exponential, so the first set increases by 1, so we just need to look at the ratio. So we have 1 divided by 1/2, which is going to be equal to 2. The next set increases by 3, so we're going to need to take the cube root of the ratio. So we have 8 over 1, so we have the cube root of 8, which is also 2. And then this increases by 2, so we would need to take the square root, so we don't need the little baby number for the square root of 32 divided by 8. 32 divided by 8 is 4, so we're taking the square root of 4, which is 2. Since 2 equals 2 equals 2, this would be exponential. The only other thing is that that number cannot be 1. So if you started doing these ratios and it came out to 1, it's not exponential. But if you are doing these ratios with these roots, if you need, and they are coming out to be the same number, it's exponential. So in chapter 1, section 1.5, it says the percent increase. Yeah, Camden. So you're on a good track, but since it says percent increase, it's just exponential. So there's no addition in an exponential format. So as long as the increase was by 3%, then you would want this. So essentially what you have, just without the plus. The first question on the homework is asking for what? No, what? Where? There should be no cosine, sine, and tangent anywhere. Let me look into that in just a second. How do you find the growth rate in values like growing by 4% per year? Growth rate is the R value. Sometimes what you can find first is the A value. So say you have 2 points that you're working with. Say you have like one, I don't know anything. Well, I guess it doesn't have to really work. It'll just be a stupid, ugly number. Let's use even numbers. 1, 10, and 3. I don't freaking know. 30. This is probably not going to be nice, but who knows? And say you wanted to know the growth rate for the exponential function involving those 2 points. What you would want to find first is you'd want to find A. To find A, we're always going to start with the equation form. And so we'd have 10 equals, don't know what P naught is, don't know what A is, but T is 1. And then we'd have, oh man, I want that to be below. 30 equals P naught A cubed. That is Not R. Wiley, JD. I have to look into that for you. That's not right. Anyway, I'll look at that in a second. Where was I? So we put these 2 points here. We're going to divide the 2 because we want to find A. So 30 divided by 10 is going to give us 3. The p-naughts cancel out, and I end up getting A squared because A cubed divided by A to the first, subtract the exponents, 3 minus 1 is 2. Square root both sides, so A is going to be equal to the square root of 3. Square root of 3 is 1.732 approximately. So this isn't the answer, though, that you want. You want the growth rate, whoever's asking that, Jack. So from here, when you have the A value, you're going to find the rate. So if A is equal to 1 plus R, then R is going to be equal to A minus 1. So if we take the A value that we have and subtract 1 from it, that'll be the R value. Now, usually it wants it as a percent. So you would move the decimal place 2 places over to the right, and so your percent growth rate would be 73.2%. In terms of the other part of your question, growing by $4 per year in that one's kind of like the first example from 1.5. If it says $4 per year, this is actually linear. Note that the word rate does not show up there at all. The word continuous rate doesn't show up there at all. So since the word rate doesn't show up, it's not exponential. This is actually a linear relationship. So you would have been given some, initial value of like $60 or something like that. I don't know, because I'm not looking at the question. So the equation you'd want would actually be 4t plus 60 because it's a linear relationship. So we want some y equals mx plus b. Our official time is over. I can stick around for a little while longer, so I'll keep answering questions. But if you have somewhere you need to be, you might want to be there. I also have a problem on a question where it says the product costs $100 today, and what would be the price if reduced by 3% per day? Okay, Savannah. So $100 today, and the price reduces by 3% per day. So not quite. So I agree that the 100 should be your P naught. Totally like that. Now this is technically 0.03, and it will be negative because it's reducing. But this is our R value. It's not the A value we need for the equation. So if A equals 1 plus R, then here we'd have 1 minus 0.03, which would give 0.97. So you'd want 0.97 to the t instead of negative 0.3 to the t. What does it mean on the homework when it says enclose arguments of functions? All that's trying to say is it's trying to say if you want to type in something like e to the 0.1t, you're going to need to input it as e caret 0.1 to the t, and it's that phrasing is what's telling you that you need these parentheses. If you were to put it in like this, Wiley will not accept it. So that's just trying to tell you that you need parentheses. So Nicole, I think I know what you're talking about. JD has a completely different issue. I think when it's talking about kind of what Rihanna was just pointing at, the thing where it says enclose things with whatever, it gives you an example of like sine of b to the x, but it's just giving you an example of the format, which you can completely ignore. JD is, I don't know what's going on with his. Anyway, there's a Wiley question for 1.5 with a graph and an S for the equation, but only gives 1 point. So it does actually give 2 points. It's just kind of hiding the second point. Yes, Rihanna, if you completed 1.5 before, I will transfer over those points. I just need to write that down. So you don't need to redo those if you did it on the last set. All right, so journey. So, you know, it looks something like this. And, you know, it gives you a full point over here, you know, whatever. But then it has a value up here. This is actually another point. It's just not quite listed in point format. This would actually be 0, 40. So if you use that idea as a second point, now you have your second point, and you can do that, you know, process of writing the two in this form and dividing the two to find A, like we did in that wolf example when we had 2 points. Did that help, Journey? Do you want me to do it more fully? My throat is making weird noises, and I really hope you guys can't hear them. Some of my questions keep saying the answers are partially correct. The format of the equation, not sure. I can look into that right now. Okay, good, Journey. I think you told me it was Journey and not like Journey or something like that, so I'll apologize if I'm saying your name wrong. I'm pretty sure it was Journey. Anyway, I'm gonna stop babbling about it. So as I'm pulling up this thing for Kira, how do you know when we use P equals, how do you know to use this versus this? I can't talk anymore, apparently. Continuous rate versus rate. So if you're reading the question and all it says is rate, then you are using the A to the T form. If you're reading it and it has the word continuous in it, even if it's not directly next to the word rate, if it says continuous anywhere in the problem, you want to use E to the KT. If it doesn't have the word continuous anywhere, you want to use A to the T. Oh, Wiley, why are you so... So Kira, on one of them, Wiley likes to do this weird thing where it changes what you input to something really stupid looking, and that's what happened on yours. So as far as I can tell from being used to it being stupid, Wiley being stupid, I believe that's the exact right equation you need, and you wouldn't have gotten the other points, the other parts anyway. This is for question 46, sorry. So I went and I pushed that through for you. So that one's fine. Other ones that are notation. Same thing for this one. Wiley, why do you do that? Based off of what I know about Wiley being a dum-dum. Yeah, that's right. So full points for that one too. So also on 1.641 was also Wiley being stupid. And the other ones that you have left seem to be different issues than just notation. So that's a thing. Yes, Rihanna?
Okay, so along with the like P naught EKT thing versus the A, so on the homework, it said it was increasing at a continuous rate of 7%. And I remember on like chapter 1.5, usually that would be like 1.07.
Okay.
But then in this, like that was marking wrong.
Right.
It said the answer was 0.07. How come there wasn't the 1 added to it?
So the values, so say, okay, let me do this. So if I say, going to the a to the t form really quick, if I say a rate of 7%, you're going to tell me that r is 0.07. But we don't have r in the equation, we have a, and a is given to be 1 plus r. So that's where that comes from. When we have the continuous rate, we change this over to a decimal like we did before, and this becomes the k value. But the k value is just the k value. So you never have to manipulate, excuse me.
Oh, okay. We can leave. Sorry.
So the continuous rate, you don't have to manipulate. It just kind of is what it is. 1.641 there. Let me pull up yours so that I have the right. One point six 1.6. Okay, so Merrick, you have a city's population of 900 is growing at 3%, so growing at 3% per year. Find a formula for the population, assuming the 3% is annual, and then we are also going to take a completely different answer, assuming it's continuous. So essentially, it wants us to find this idea in both forms. Like we're going to take the first one where we're just having an a to the t, and then we're going to take the second one to have the rate being continuous. So, well, 3% is equal to 0.03. So in the a form, in the, let's kind of, whoa, what have I done? So we've kind of got two situations going on here. In the a to the t form, that gives you your r value, right? If it's just a regular old rate. But then we have to find our a value, which is 1 plus r, so 1.03. And that's what we'll use in the equation. Now, P naught, the initial condition, is going to be our initial value of 900. And then we just found our a to be 1.03 to the t. But then in part B, you're asked to say, okay, well, now it's no longer just a general rate. Now it's a continuous rate. But it's still a continuous rate of 3%. So now we have that the k value is 0.03. But as I was just kind of noting to Rihanna, you don't have to manipulate the k value at all. When it's a continuous rate, it's just that number. So we'd have that equation would be 900 e to the 0.03t. And you would want to write that into Wiley like this. In part B, you're then asked to estimate the population in 15 years. So you're going to take each one of these equations and you're going to plug in 15 and use those numbers. So I'll let you mess with that a little bit. Let me know if you're still not getting it while I answer this other question. Two of mine that I can't figure out the right format. Doing it wrong. Okay. What do you, stop it. Sorry, my cat. Stop. Mazda. Yes, stop it. Come here. Ready? Yes. Sorry. 08. Yeah, that one's throwing off lots of people. So let's see, what do we got here? We've got, it's one of these ones. So we've got 4, we've got 216. So this is an exponential equation. So we're going to want some p naught a to the t. So our P naught is going to be our initial condition. What do you think my P naught is, Abby? Yep. All right, so now we need to find the A value. So to find the A value, we have to do that kind of gross process of finding the two equations and dividing them, because we essentially have 2 points here. We have 0, 4, and we have 2, 16. So if you know what, can you still hear me? Cool, because that is bothering me. Okay, so we have 2 points, 0, 4, and 2, 16. So if I write them both in this format, well, equal to P, we'll have 16 equals, I technically know what P naught is, but I don't need it, so let me just not write it. If you'd rather put it in there, you can totally do that. And we have 4 equals P naught A to the 0, and we're going to divide these two equations. The P naughts cancel each other out. 16 divided by 4 is 4. And A squared divided by A to the 0 is going to be 2 minus 0 is 2, so we still get A squared. Square root both sides. Algebraically, you'd get plus or minus 2, but A can't be negative, so it would just be positive 2. Now that you have your P naught and your A, you can write your equation. So we'll have 4 times 2. Let me double check your past attempts, because, no wait, you have an X. Never mind. Some people were using T's and that's what was throwing it off. Yeah, you were kind of focusing on a linear relationship when notice that that line isn't perfectly straight. So since that line isn't, no, wait a minute, you had it on attempt 2. Yeah, you just had a T instead of an X.
Okay, yeah, I was wondering, I think I did put in a T. I can't look at it now because I'm on a different one, but okay, I'll go back and I'll put in an
I
X.
just pushed through the full credit for it, so you can go back and fix it if you want, but
okay.
Because yeah, it was just an X instead of a T.
Okay.
And then 1.734. The last one. Let me stop this recording. I realize I'm still going.